Bismillahirrahmanirrahim. In this video we are going to discuss uniform PWM for the full bridge single phase inverter. The circuit diagram for the full bridge single phase inverter is shown in front of you, and the gating signals and the waveforms are shown on the left side. In uniform PWM we have a carrier waveform, that is this triangular waveform or the carrier signal. It is compared with the reference waveform. So our reference waveform is the square waveform that you can see over here, a constant reference for the positive cycle and a constant reference for the negative cycle. So this is the rectangular waveform, that is the reference signal, and the frequency of this reference signal will be the frequency of the output or the fundamental frequency. So reference signal is of fundamental frequency or the frequency that we desire at the output, and the carrier is of high frequency that is shown over here. In this particular case, the carrier frequency is 10 times higher than the fundamental frequency, because in one cycle of the output waveform there are 10 cycles of the triangular waveform. So we define a term frequency modulation index or frequency modulation ratio, that is defined as the ratio of the carrier frequency with the reference frequency and is represented as MF. The second term that is commonly used, that is the modulation index, that is defined as the ratio of the magnitude of the reference waveform and carrier waveform and is represented as MA or the capital M. So by changing the modulation index, we can change the width of the pulses. How the pulses are generated? By the comparison of the reference signal and the carrier signal. So if you look at this part, this pulse, this is generated by the comparison of this carrier and the reference waveform, right? So the pulses are generated by the comparison. So whenever your reference rectangular waveform will be higher in magnitude with respect to your triangular waveform, you will get a logic high. So here are the pulses which are applied to one pair of the switches, and that pair of the switches S1 and S4. So switch S1 and S4, they are turned on by the application of these gate signals. And in the negative cycle, there is no gate pulse for the switch S1 and S4. For the negative half cycle, we have the pulses which are generated by the comparison of the negative part of the rectangular waveform and the triangular waveform in that section. So that you can see over here, this is the gate pulse which is generated by the comparison of the triangular waveform and the reference waveform. So these gate pulses are applied to the switches S2 and S3. So consider it 2 or 3 with respect to our diagram that is used for the single phase full bridge inverter. Okay, when we apply the gate pulses to the switch S1 and S4, we will get the positive voltage across the load terminal, because our point A will be connected with the positive terminal of the source. So our output voltage will be equal to plus Vs when our switch S1 is turned on, and when they are turned off, zero output. When they are turned on again by the application of the gate pulse, we get plus Vs again, and so on. Whenever gate signal will be applied, we will get plus Vs voltage at the output. It is basically a class D amplifier. Whatever is the gate signal that is amplified, its shape is retained, and we get an amplified voltage Vs at the output. These pulses are applied to the switches S2 and S3, and when they are turned on, the load voltage is negative because point B is connected with the opposite terminal. Okay, so point B is connected through S3 to the positive terminal, and point A is connected with the negative terminal. Over here A is connected, and through S3 point B is connected. So point B is now positive and point A is negative. So the load voltage is of opposite polarity, minus Vs, with respect to our first half cycle. So this is the output voltage waveform that we obtain by applying these gate signals. One of the purpose of using this uniform PWM is to control the output voltage, because if you increase the magnitude of the reference waveform, let's suppose it is increased to this level, you will see the width of the pulses will increase. The width of all the pulses will change equally. That's why we are going to call it uniform PWM. All the pulses have the same width, right? So when we increase the magnitude of the reference waveform, reference signal, our output voltage will increase. Why? Because more area will be covered by these gate pulses, and resultingly the more area will be covered in the output voltage waveform. So if our modulation index goes high, that will increase the output RMS value because more area will be covered. So more area will be there, that will result in the high RMS output voltage. So with the help of uniform PWM, we can control the output voltage by controlling the magnitude of the reference waveform. That is the modulation index. Okay. Now let's look at that how much output voltage will be there in terms of RMS. So this is our output voltage waveform. Okay, before discussing the RMS, let's discuss that what is the time period of the carrier waveform. So let's suppose that there are P number of pulses in half cycle, P number of pulses in the negative half cycle, right? So total number of pulses are equal to 2P in one output cycle. So what will be the time period of one cycle of the carrier waveform? In the half cycle there are P number of pulses, so total angle for the half cycle is P, so divided by number of pulses, this will be the angle for one carrier cycle, right? So in terms of angle, this width is pi by P, and your pulse will be centered of that time period, right? So this will be pi by 2P, the center point of that. The total length of this is pi by P, from 0 to pi by P, if we consider the very first pulse. Similarly, this will be 2 times of pi by P for the second pulse, and for the third pulse it will be 3 pi by P. Every pulse has the time period, is the portion of a carrier signal whose time period is pi by P in terms of angle, and that pulse will be centered of, will be aligned at the center of that switching interval. Okay, so now let's assume that the width of the pulse is del, right? So I am going to sketch the zoomed version of that pulse over here, which is centered at the interval of pi by P. So this total interval is pi by P, and this point is pi by 2P, and let's suppose the width of the pulse is del and the magnitude is plus Vs. So this is our pulse, and this pulse has its replica, its image in the negative half cycle. So you can see that this pulse is the replica of that one, image of that one, inverted image. Similarly, for the second pulse, we have the image over here, and for the third pulse, we have this image, and so on. Every positive pulse has the equivalent negative part, right? So I will be considering one pair of the pulse now. This and this makes one pair. Similarly, this will make a second pair. So there will be p number of pairs, because we have assumed that there are p number of pulses per half cycle. So total number of pairs will be equal to p, right? Okay, now let's evaluate the output voltage waveform by considering the pulse pairs. Okay, V naught will be equal to 1 by 2 pi for the average. As our pulse is centered at pi by 2 pi, so what about this angle? The starting angle of the pulse. Pulse is equally distributed. This is del by 2, this is also del by 2. So this angle will be pi by 2p minus del by 2, and this edge will be at the angle pi by 2p plus del by 2, right? So integrating from pi by 2p minus del by 2 to pi by 2p plus del by 2, and what's the voltage level? Vs, and we are calculating the RMS, so taking the square of that one, integrating with respect to the angle. So we will get the area covered by the first pulse. It has its equivalent negative image, that is this one. If I am considering this pulse, so it's negative. So to get the total, I am going to multiply it with 2, because its equivalent negative pulse is going to be there. And how many pulse pairs are going to be there? P number of pulse pairs. So I am going to multiply it with P, and then I am going to take the under root to calculate the RMS value. Okay, now if I simplify this expression, so what I am going to get, we can take Vs out, 2 and 2 will be cancelled out, so we will be left with P by pi, and if we apply the limits, so pi by 2p plus del by 2 minus pi by 2p plus del by 2. So our output voltage RMS value will be equal to Vs into P del by pi. So that's the expression for the output RMS value, and you can see that output RMS value depends upon the width of the pulse. Del is the width of the pulse, right? So del is the pulse width. So if we change pulse width, our output voltage will change, and P is the number of pulses, pulse pairs, right? So we can calculate the output voltage of this inverter, which is being operated with the uniform PWM. Now let's look at the Fourier series representation of the output voltage. So for that, now I am going to consider these angles. Let's suppose that this is our pulse, and we consider this pulse. Let's suppose that the width is del for this pulse, and it is at angle alpha 1 from our reference. This is our reference line. From this reference, the starting angle is alpha m, right? Okay, so let's write down the expression for Fourier series. Okay, first of all, let's decide about A naught, the DC component, that will be 0, because we have the equal positive and the negative area. And as this signal have the half wave symmetry as well as the quarter wave symmetry, so your AN will also be 0. Only BN will be there, and that will exist only for the odd harmonics because of the quarter wave and the half wave symmetry. So for this voltage waveform, now I can write down an expression to calculate the Bn considering the first pair of the pulse. So how to calculate that one? It will be equal to 1 by pi integration from alpha m to alpha m plus del. So starting angle is this alpha m, and as the width of the pulse is del, so this will become alpha m plus del. So the area of this pulse is covered, right? And the magnitude in between is Vs into sine of n omega t while calculating the Bn. And integration is with respect to omega t because we are taking the limits in terms of angle. Then taking its negative part, so for that I can write minus integration of Vs into sine of n omega t with respect to d omega t. What will be the set of limits? For its image is this one, and its image will be at the angle defined over here with the addition of pi. So this will be pi plus alpha m, the starting angle of that pulse, this one, and as the width of the pulse is del, this one, so this angle will be equal to alpha m plus del, that was the angle over here delayed by pi. So we will be integrating up to alpha m plus del by plus pi. Okay, now let's simplify this one. So Bn will be equal to, let's take Vs common out from here, and n pi, so we will be having minus cos of n omega t, and we are going to solve it for the limits from alpha m to alpha m plus del. Then the second part is minus cos of n omega t, solving it from alpha m plus pi to alpha m plus del plus pi. Okay, so now let's simplify further. Bn will be equal to Vs by n pi, and applying the limits I can write it like that, minus cos of n alpha m plus del plus cos of n alpha m plus cos of n alpha m plus del plus pi minus cos of n alpha m plus pi. Now using the basic trigonometric identities, I can write this one as like this, cos of n alpha m plus del plus cos of n alpha m. So there is the addition of pi over here, so this term can be written like this, minus cos of n alpha m plus del using the basic trigonometric identity plus cos of n alpha m, right? So now this can be written as Bn equal to 2Vs by n pi cos of n alpha m plus del plus cos of n alpha m. Now let's use the trigonometric identity. Using trigonometric identity, that is cos of alpha minus cos of beta, that can be written as minus 2 sine of alpha plus beta by 2 into sine of alpha minus beta by 2. So let's consider that this is alpha and this is beta. So this Bn now can be written as 2 into Vs by n pi into minus 2 sine of n alpha m plus n alpha m plus n del by 2 into sine of n alpha m minus n alpha m minus n del by 2. Now Bn can be written as minus 4 Vs by n pi into sine of n alpha m plus del by 2 into sine of minus n del by 2. And then now using that sine of minus theta is equal to minus sine theta, I can further simplify it. Bn is equal to 4 Vs by n pi into sine of n alpha m plus del by 2 into sine of n del by 2. So this is the Fourier series coefficient Bn for the one set of pulses. Means considering one pulse, this one and this one pulse set, positive and the negative part. Okay, now this is to be repeated for every pulse. As the width of the pulse is same, so we can write, we can find out the Bn for every pulse, and there will be p number of pulse pairs now. So the net Bn will be equal to summation m from 1 to p, where p is the number of pulse pairs, 4 Vs by n pi into sine of n alpha m plus del by 2 into sine n del by 2. Right? And now how we can represent the output voltage in terms of Fourier series, that will be equal to this one. N is an odd number, the net Bn into sine of n omega t. So from here I can say that V naught is equal to summation over all odd harmonics. And what is the net Bn? Bn is also a summation. So that is the summation over m. M is varying from 1 to p, 4 Vs by n pi into sine of n alpha m plus del by 2 into sine of n del by 2. And this will be multiplied by sine of n omega t. Right? So we have developed the Fourier series representation for this output with uniform PWM. Right? Okay, now let's look at some other parameters. If I say the time period of the output waveform is t, what will be the time period of one switching cycle? So let's state it over here. So output waveform time period, let's suppose that is equal to t, then switching waveform or the triangular waveform time period can be calculated by having the information of frequency modulation ratio. So that will be T by MF. Okay, now what will be the pulse width? Okay, now let's draw one switching interval, one cycle of the triangular waveform, and we are comparing it with the constant reference. And by the comparison, we are going to generate the PWM pulse. So the pulse will be there in this section when our reference is higher than the triangular waveform. Now if I increase this reference and bring it over here, the width of the pulse will be increased. And if this reference becomes equal to the carrier, this is the carrier, the magnitude is AC, and this is the reference AR. So if I increase the magnitude of the reference, and if the reference magnitude becomes equal to the carrier, the pulse width will be equal to the switching time period. So pulse width is related to the modulation index. If the modulation index is 0, then your pulse width is 0. And if the modulation index is 1, then the pulse width is equal to the complete switching cycle. That's the triangular waveform. So we can write the pulse width in terms of the modulation index, that is, pulse width will be equal to m into Ts. And what is Ts? Basically Ts is this one switching interval, right? And this is in terms of angle. You can also calculate it in terms of time by using the basic relationship that theta is equal to omega t. So time will be equal to theta by omega, right? Okay, so after calculating after having this expression, if I want to write it in terms of time, so it should be del by omega. Basically, if I consider Ts in terms of time, so if I want to find out the width in terms of time, so it will be del by omega, that will be equal to m into Ts. Right? Okay. So pulse width in terms of time or in terms of angle? In terms of angle, it is simply m into Ts, where Ts will be considered in terms of the angle. So I am going to write it over here. If this is in the form of angle, this will be in the form of angle. Okay. Now let's look at the starting and the ending time. So let me remove these writings first of all. So this is the starting time of the pulse. So I am going to mark as TMS, and this is the ending time, this is TME. We can write in terms of time or we can write in terms of angle. Starting angle is alpha m, the width is del, and the ending angle is alpha m plus del, right? Or in terms of time, we can use the expression theta is equal to omega t, and we can convert angle with respect to the frequency into time. Okay, now what will be the expression for calculating this time? So the starting time of the pulse, that is equal to alpha m starting angle divided by omega, So that is given as m minus capital M into Ts by 2, where m is equal to 1, 3, 5 up to 2p, and the time for the end of the pulse will be calculated alpha m e is just indicating the end divided by omega, that will be equal to m minus 1 plus capital M into Ts by 2, and in this expression m varies as 2, 4, 6 up to 2p. So these two are used to calculate the starting time and the ending time. This is, you can say, Tm start, and this is the Tme, or you can calculate in terms of angle. Okay, now let's represent the same expression in terms of pulse number. So in terms of pulse number, capital P, the Tm can be written as Tms will be equal to alpha ms by omega, that will be equal to 2 capital P minus 1 minus m into Ts by 2, and the ending time Tme, that is equal to alpha m e by omega, that is equal to 2 into capital P minus 1 plus m into Ts by 2. So P is equal to total number of pulses in the output waveform cycle, in one cycle, positive plus negative. And in this P varies from 1, 2, 3 up to 2 times small p, because small p is the number of pulses per half cycle, as we used earlier, right? So in this way we can calculate the starting angle and the ending angle of the pulse, or the starting time or the ending time of the pulse. You can also calculate the ending time or the ending angle of the pulse by adding the pulse width in the starting angle or starting time of the pulse. So you can write down the expression for that. Okay, so we have discussed the uniform PWM in detail, and we have looked at how we can calculate the output RMS voltage and how we can represent the output voltage in terms of the Fourier series. In this discussion, we use the triangular waveform as a carrier. The other carriers are also used, for example, the Sawtooth waveform. Sawtooth waveform can be used as a carrier. So now if I discuss with respect to the Sawtooth waveform, so let me draw the Sawtooth waveform. Let's suppose that there are 3 cycles of the Sawtooth waveform in the positive cycle, and then 3 pulses in the negative cycle. And I am going to compare this Sawtooth waveform with a reference. This is AR, and this is AC. And let's suppose that there are 3 cycles of the carrier waveform in first half cycle of the output, and this is the negative cycle. So negative cycle, and this one is the positive cycle. Okay, so pulses, those will be generated, will be applied to the switches. So the pulse generated over here is this one, and this will be applied to switch S1 and S4, right? Positive half cycle. And for negative half cycle, we will be using these switches S3 and S2. So S1 and S4 for positive half cycle. So S1 and S4 are turned on by these gate signals, which are generated by comparing a Sawtooth waveform with the rectangular waveform or the constant one. So all of these pulses will be of equal width. Now let's draw the pulses for the negative half cycle, means which are applied to the switches S3 and S2 as a gate signal. So this is the pulse. Similarly, by this comparison, this pulse will be there, and we will be having a pulse over here, and then the positive cycle and so on. So what will be the output voltage waveform? The output voltage waveform, if I sketch, so when we turn on S1 and S4, this will be plus Vs. Then during this interval we will be having this pulse of magnitude plus Vs, and over here plus Vs. So plus Vs in the positive half cycle and minus Vs in the negative half cycle. Right? So this will be our output voltage waveform. So we will get these pulses in the positive half cycle and these pulses in the negative half cycle, and this will be repeated, right? Okay, so let's take one pulse over here. Let's suppose that the starting angle is alpha m and the width of the pulse is del. So what will be the ending angle? This will be alpha del m plus, alpha m plus del. So if I calculate the output RMS value of this one, that will be exactly same that we have already calculated. That is V naught equal to Vs into P into del by pi, where this is the small p, number of pulse pairs, right? Okay, and what about Fourier series representation? If you look at the angles are exactly same. The starting angle is alpha m, ending angle is alpha m plus del, and the width is del, and we have the replica of this pulse in the negative part. This is one pulse pair, the second pulse pair is over here, and the third pulse pair is over here, and if we have more pulses they will exist in the pairs. So the Fourier series coefficient will be same. So Fourier series representation will be same, either it's the Sawtooth waveform or the triangular waveform. So the Bn for this waveform will be equal to m is equal to 1 to p number of pulse pairs. So 4 Vs by n pi into sine of n del by 2 into sine of n alpha m plus del by 2, and the total output can be represented like that for all odd harmonics up to infinity, Bn into sine of n omega t. Okay, now what will be the expression for starting time or angle of the pulse? So let's look at this pulse, and for that I can say the Tm, the time, that will be equal to alpha m divided by omega, that will be given as m minus capital M into Ts, right? So where m is the pulse number, or the starting edge of the pulse, and this one is the modulation index. What will be the ending angle? Ending angle will be the end of the switching cycle or the Sawtooth waveform. So if you know the pulse width del, and how to find out the pulse width del, that will be equal to modulation into Ts, where Ts will be considered in terms of angle. So pulse width can be, in terms of angle, can be determined from here. So if you know the starting angle of the pulse, by adding the pulse width in that one, you will get the angle for that one, or that will be, if you consider p number of pulses per half cycle, so this will be pi by p, and the end of this one will be 2 pi by p, the end of this one will be 3 pi by p, and as p is equal to 3, so it will be pi. So ending angle is already known, so starting angle can be calculated in the number of ways. One way is to use this expression, or the other way is that if you know the width and you know the ending time is over here, that is pi by p, the switching cycle of your carrier waveform, Sawtooth waveform. So subtracting the pulse width from that, you will get the starting angle, or you can convert it into the time. Okay, so we have analyzed in detail the uniform PWM, and we have seen the triangular carrier, and we have also seen the Sawtooth carrier. There is no change in the voltage, no change in the spectrum. Then why we are using that one? Sometimes the implementation of the Sawtooth waveform in your microcontroller is easy. You can easily implement this Sawtooth waveform using the timers. So one timer is running from 0 to certain maximum value, and then it is reset. Then it is running again, and then it is reset. So implementation of the Sawtooth waveform, digital implementation, is easier as compared to the triangular waveform. So sometimes for the control of the voltage in uniform PWM, Sawtooth waveform is used, because it can easily be implemented using the timers of your microcontroller, and it gives you the same result, because you can control the voltage by increasing this reference over here that you are going to compare with the timer values, or with this Sawtooth waveform. You can change the width of the pulse. You can change the width of the pulse. Okay, so over here one last thing that I want to tell you, that I have considered the direct Sawtooth waveform. So with the increase of the reference, your modulation index will be decreasing. So it should be considered like that. Inverted Sawtooth waveform. So if you consider the inverted Sawtooth waveform, so I am going to draw it again over here. Let's suppose that this one for first half cycle pi, and then like that. So now if I make a comparison of this waveform with this reference, so by increasing the reference, our pulse width will be increasing. So if it is moved to this one, you can see the pulse width will increase. So with this waveform, these expressions will be valid. Otherwise, you will have to take the difference with the one. Okay, so that was all about the uniform PWM for the single phase inverter circuit. Thank you very much.